Let's talk about closed sets. That's what I would like to discuss this morning. Closed sets. Sure, you all know on Zoom you should probably stay muted, but please feel free to shout out if you have questions about something. I would be interested in hearing about it. Let's talk about closed sets today. First of all, the big fact that hopefully you remember from real analysis: closed. Everybody knows this. Closed is not the opposite of open. Right? Closed and open mean different things, and they're not. Closed does not mean not open, and open does not mean not closed. In the textbook, there's a math joke about this, and the joke is, I'm not making this up. It says, how is a door different from a set? And the answer is, a door is either open or closed, but a set can be open or closed, or neither or both. To me, this is not a joke. That's just like me saying, okay, in set theory, in topology, closed and open are not opposites. That doesn't make it a joke. You could probably make that into a joke somehow, but that doesn't count, in my opinion. Anyway, it is true. A set can be open, or it can be closed, or it could be neither, or it can be both. And so what does it mean to say the definition of close is not just not open, right? What is the definition of close? So in analysis, closed means that it contains all of its limit points, right? That's the standard way that we talk about closed sets in analysis. But actually, the definition of limit point is a little complicated. It means something about epsilon neighborhoods or whatever. So actually, the standard notion of limit point is not the nicest way to talk about closed sets in an abstract topological space, because we don't have the epsilon neighborhoods to, it's not convenient to talk about points which approach some other point in a sequence, which is kind of what limit points are about. So, but I hope you remember there was a theorem from real analysis about the relationship between closed sets and open sets. Anybody happen to remember? There's a theorem about, like, if something or other is an open set, then that means something else is automatically a closed set. This is a relationship between the concept. It's not that closed and open are the opposites of each other, but anybody remember what I'm talking about? Yeah, Alvin.
Isn't it like it's a complement or something?
Yeah, right. The complement of an open set is closed, and the complement of a closed set is open. So this is a theorem from analysis. The complement of an open is closed, right? That's a theorem, and the complement of a closed is open. So those are theorems from real analysis, which you prove using, things about limit points. But actually, without the concept of limit points in an abstract topological space, this is taken to be the definition of what closed means. So we define a closed set to be the complement of any open set. So I'm going to write that as my definition. It's just turning that theorem, which in real analysis you prove that, but in topology it's just taken as this is what the word closed means. So the definition is, I'll say let X be a topological space, and a subset of X a subset, then A is closed when the complement X minus A is open. That's the definition of closed. So closed means the complement is open. And the complement is kind of like the opposite of a set. It's everything which is not in the set. So in that sense, closed and open refer to opposites on some level, but it's not that the concept of being open is not the opposite of being closed. All right. In the real numbers, closed sets, in R, closed sets, in R, the standard topology, open sets look like open intervals or unions of open intervals. Closed sets, you can imagine them as looking like closed intervals. But actually, there's other sort of significantly different things that a closed set could look like. So they look like closed intervals, or just like individual points in real individual points. All right, like a single point by itself is a closed set in the real numbers, or just some kind of finite, like 10 points taken together, 10 separate points as a set. That's a closed set because the complement of it is an open set, is a bunch of open intervals. Or even weirder things can be closed sets in R, or I will just say weirder stuff like the Cantor set is a closed set. The Cantor set, remember, is that thing where you start with the interval, but then you remove the middle of it, and then you remove the middle of the two pieces that you had remaining, and you keep on doing that. You get some kind of weird fractal-like set. All right. That's a closed set too. So generally speaking, if you ask me to imagine in my mind a closed set, I do think of a closed interval, but although that's not always what a closed set looks like, but it looks like some of those things. All right. What about in R2 or Rn or something like that? In Rn, well, let's talk about R2 just so that we can draw some pictures. A closed set. What does a closed set look like? Remember last time we drew a bunch of pictures of what an open set in R2 looks like. Basically, it looks like a shape without its boundary, but the inside of a shape. That's what you should think of a typical open set looking like. A closed set. Again, closed sets can be very weird, but there are certain ones that you can think of that are not so weird. A closed set might look like, so a closed interval in R, the analogous thing, the similar thing to that in R2 would be ball, like we talked about last time. So a closed set might look like what we call a closed ball. And the closed ball is written this way, B of x epsilon with a bar. Generally in topology, the bar indicates closedness, or there's an operation called the closure, which we're going to talk about eventually, which the bar represents. But when you see a set with a bar on it, that is generally indicates that is a closed set. The closed ball, and actually, can I just say the definition of that? It's all the points in R2, or let's just say Rn, because it doesn't really matter the dimension, where the distance from x to that point is less than or equal to epsilon. All right, so the picture you should have, if this is x, the closed ball around x is all of these nearby points where this set has radius epsilon. I should have, sorry, that's hard to see. That's the radius, is the epsilon. All right, this is the closed ball. The open ball is what we talked about last time, and usually if I just say ball, I usually mean the open ball. If you're talking about the closed ball, you say closed ball. This is the closed ball. The only difference between the open ball and the closed ball is the inequality sign right here. For the closed, it is less than or equal to. The or equal is how you additionally get the points right on the boundary here. And those points are missing from the open ball, that's the important thing about determining whether this thing is open or closed. All right. So a closed set might look like a closed ball, or another sort of typical standard closed set would be a closed rectangle, you know, like this, something like that. That's also a closed set. And a closed rectangle, if you wanted to write the definition, I mean, a closed rectangle is just a product of two closed intervals. Right? You think of this as being a closed interval in the x-axis and a closed interval in the y-axis, and then you take the Cartesian product of those as sets, means all the pairs where the x-coordinate is in that interval and the y-coordinate is in that other interval. All right, these are typical closed sets, or they can look like much weirder things. There are other weird-looking closed sets, but these are the ones. If you ask me to imagine a closed subset of R2, I'm thinking probably this will be the picture in my mind, even though it may not actually look like that. All right. We're going to draw some more pictures in a moment, but I thought, let's just, for fun, let's try to demonstrate. Let's prove that this closed ball really is closed in R. Let's do Rn. The R2 is what you should have in mind, but actually the proof, the 2 is not used anywhere in the proof. The closed ball is closed, all right? What do you have to demonstrate to show that something is a closed set? You have to show that the complement is open, because that's the definition of what closed means, all right? So I'll say we must show that Rn minus b bar x epsilon is open. All right. And so the picture that you're imagining, you know, here's the picture of the closed ball, right? It's supposed to be a circle. Sorry. I can make a real circle with this thing. That's right. All right. So this is b bar of x and epsilon. What does the complement look like? Rn minus b bar of x and epsilon, it looks like everything outside of that circle. And now, since this circle also includes its boundary, the complement includes everything outside of that circle, and the complement does not include this boundary because the original set does include the boundary. The complement does not include the boundary. So the complement looks like, I do this? I have a dotted line pencil. Isn't that great? The complement is this, everything out here. Right? This is Rn minus b bar of x epsilon. Everything outside the circle. All right. And the original closed ball does include the boundary, and so the complement here does not include the boundary. And what we have to demonstrate is that this set over here is open. Now, remember what open means. Well, I'm talking about the standard topology, of course. The best way to think about demonstrating a set is open or not is you choose any point in this set, and can you put a little ball around it, a little neighborhood around it, which stays within that set. So can we just think like just on an intuitive level, if I choose some point over here, I'll call it y, just because this point here is x, and I don't want to call it x also. Can you see? I mean, is it true that you can put a little neighborhood around y, which is still fully contained inside the complement? I think the answer is yes. I mean, you should be able to make a very small neighborhood. Now, if you actually want to prove that, in this example, it's not so hard to actually prove that. You just have to describe, okay, how exactly small do I need to make this little neighborhood in order for this to work out? So the idea is there is an open ball around y, which is still fully contained inside that complement. So can I just say we need to find a little ball around y. Really, it amounts to something like we need to find delta greater than 0 such that the ball around y of radius delta is contained in this complement set, Rn minus b bar x epsilon. I use delta just to represent this radius of the little blue neighborhood there. Maybe I'll draw the delta in blue so you can tell. All right, it's the radius of that. As long as we can demonstrate that there really is such a delta, then everything's going to work out great. And how would you choose that delta? I would say if we think about these 2 points, x and y, maybe I'll just for clarity, I will redraw. We have x inside this circle, and then y is like over here somewhere. Right, and that distance there is epsilon. Would anyone want to suggest how could you define what the delta should be? You have to make it so that you are sure that the neighborhood around y does not reach inside this dotted circle there. Anybody got an idea? You need it to be like this small, not that big, right? You want the delta to be not too big. Can I say it in terms of epsilon, maybe in terms of something else?
I'm not exactly sure what it is, but is it something like to do with the distance between x and y?
Yeah, it also involves the distance from x to y, so maybe I'll label that on the picture. Good idea. That would be, this much, right? And I'll write that as distance from x to y, d of x and y. Yeah. So it should involve that. What do you want to choose to be the delta then? Anybody else got an idea?
Would you also have to subtract epsilon from that?
Yeah. I think actually that'll do it. If I take this distance and then subtract epsilon, distance from x to y minus epsilon. Yeah. Yeah, so on my little diagram here, that would be this. That's the delta. Are you sure that is greater than 0? I said the delta has to be greater than 0. You should be, I suppose, a little worried that since I use a subtraction here, maybe it becomes negative. But this epsilon is less than the distance from x to y. That's because y is outside of this ball, which means the distance from x to y is more than epsilon, right? Because that's what this open ball means, or that's what the closed ball is. All the points distance epsilon or less. If y is outside of there, it means the distance is more than epsilon, which means this is going to be greater than 0. All right. Then I'll just say then all points in ball, the open ball around y of radius delta are outside the closed ball x of radius epsilon. And therefore, what that means, another way of saying that, is that this little blue ball is part of the complement. It is a subset of the complement. None of it goes inside that set. It's all outside that set. So ball around y of radius delta is a subset of Rn minus the closed ball around x of radius epsilon. There you go. That's what we wanted to show. This is how you show a set is closed. You have to show the complement is open. And usually you show something is open by showing that every point in there has a little neighborhood around it. All right. So a closed ball really is a closed set. Would you believe me if I told you, although I don't want to go through the proof of this, but also a closed rectangle, what we call a closed rectangle, you know, AB cross CD, is closed. It really is a closed set. So when you call it a closed rectangle, that's not a bad thing to call it because it really is a closed set. If you want to think about that, just think about, here's the closed rectangle. All right, what does the complement look like? The complement would be this open rectangle and everything on the outside of it. And then is that thing an open set? You ask yourself, if I just choose a point out here, can I make a neighborhood around that point which is still outside of the rectangle? And the answer is yes, because the rectangle here doesn't include its boundary. This being outside of there means, yes, you can find a little neighborhood out here which doesn't reach inside of the rectangle. All right, same idea. I don't want to go through all the particular geometric details, but it's the same basic concept. All right. I have just a bunch of examples of closed sets, and then that's going to do it. I don't think we're going to go to the whole time today, if that's all right. I'm still not feeling very well. I got a bunch of pictures of sets in R2. We can just draw the set and say, is it closed or not? This is the old, is it closed or not game. Is it closed? How about, these are all sets in R2. How about like a curvy line segment in R2? Is it closed? What you should imagine in your mind is, I consider the complement of that set, everything that's not part of that line, and then try to make a little neighborhood around a point outside there. Does every point outside, another way of thinking about it is just, if you choose some point outside of that set, can you make a little neighborhood around it that is completely outside of that set? And I think in the case of this line, the answer is yes, you can do that. Any point that's not on that line, you can put a neighborhood around it so that that whole neighborhood is not on the line, is not intersecting with the line. All right, so this, it is closed. All right, and the way that I think that through is just any point in the complement, or maybe using even plainer language, any point outside the set has a neighborhood outside the set. That's what closed means, really, if you want to think of it in terms of neighborhoods. Any point outside the set has a neighborhood outside the set. Okay, how about, that was my first simple example. How about similar line, but it has some loop-de-loops in it. Is this closed? Again, you ask yourself, is it true that any point outside of this set has a little neighborhood that remains outside of the set? What do you think? You want to show me the thumbs? You can do real thumbs. You can click the zoom thumbs if you like. I know Zoom has thumbs. I see some thumbs up. Yeah, I guess I wasn't clear on what the thumb up means. The thumb up means yes, it is closed. The answer here is yes, it is closed. The loop-de-loops don't really matter in this example, right? Even if your point, you choose some point outside of the set. Now they could be like enclosed in one of those loop-de-loops, but it doesn't matter. You can still make a small neighborhood around it. So this set is also closed. Oops. Is closed. Yeah, great. How about something like this where it has the loop-de-loop, but the loop-de-loop is filled in? All right. Is that still closed? Again, you think about, choose a point outside of the set. Does it have a neighborhood which is entirely outside of the set? I think the answer is still yes, this is still closed. Filling in the loop-de-loop doesn't change much. Actually, filling this in only removes things from the complement Anyway, this is still closed. Because if you choose, again, any point that you choose out here, it has a neighborhood that is fully outside of the set. All right, how about, okay, here's a strange, I want the same set, but the loop-de-loop part, I erased the boundary of it. This is very weird looking, but it's the same set, but I took away the boundary of the loopy. I used just the inside of the loop, not the points along the boundary. Is that closed? Again, you think about if I choose some point outside of there, does it have a neighborhood that's completely outside? Or are there some points outside where every neighborhood around them has to stretch into the set somehow? Any thoughts about that one? I see somebody clicked the zoom. No. Yeah, the answer here is no. It is not a closed set. Can you tell me, maybe can the clicker tell me, where would you choose a point which has neighborhoods, has no neighborhoods that are completely outside of the set?
I'd choose it like next to the loop.
Yeah, like on this sort of boundary region, right on there, maybe. That is a point in the complement. So this point is in the complement, but all the neighborhoods around that point have to stretch into the set somehow. So this point here, this, come on, shrink it. Yeah. This point has no neighborhood contained in the complement. All right. That means the complement is not open, because open means every point has a neighborhood inside of the set. So the complement is not open. So the set is not closed. All right. And this set, by the way, is also not open because there are points in the set with no neighborhood that's contained in the set. For example, if I chose, say, this point, just some random point on this part of it, then that point has no epsilon ball, which is totally contained inside the original set. And so this is not an open set, and it's also not a closed set. All right. Great. How about, any questions about that one? That was a little strange. How about typical closed set, is like a closed ball or a closed rectangle, but it could be some other closed blobby type shape, something like this, or maybe even a shape with some holes in it. This one is a closed set, as long as you include this boundary here of the outside. And also in this example, you need to include these hole boundaries, the boundaries of the holes on the inside. But this one also is a closed set, because if you consider any point in the complement, it has, like, any point outside of that set would be something out here, or even maybe in here. Such points always have little neighborhoods which are still completely outside of the set. All right. Great. How about some slightly weirder example? Oh no. Yeah, sure. How about this? This is a set of 6 points in the plane. Is that a closed set? Just those 6 points. Is that a closed set? I see some nodding of the heads. The question you should be asking yourself is, if I choose some point outside of those, just like any point which is not one of those 6 points, I guess, can you make a neighborhood around there which avoids the 6 points? Yeah, you can. It might have to be pretty small, but yes, you can. So this one is closed. Right. What about how about this one? Here's a fun one. This is a line together with all the points on one side. This is called a half plane. Is that a closed set? The same thought should be in your mind. If I choose some point outside of there, which I guess would have to be on the left side of the line, then is there a neighborhood around that point which avoids the set entirely? The answer is yes, there is. All right. So this is also closed. This kind of set which I drew there is called a closed half plane. You could also talk about an open half plane would be one where the points on the boundary are omitted. That would be an open half plane, and that is open and not closed. Do you have a question, Alvin?
Yeah.
Sorry about that.
What about the other side? Like, is it an open boundary, or is it like
The
like
other side?
Like one side has the line, and then the other side is like infinite, or
Yeah, right. That's what I mean by half plane. It goes on forever, up and down and to the right in this picture. Yeah. Okay, how about, I just got a couple more of these. How about a whole bunch of vertical lines? Let's just say like infinitely many. Just imagine like you have R2 on a piece of graph paper and your set is just all of the vertically drawn lines on the graph paper that go, infinitely far. All right, just the vertical lines. Is that a closed set? Again, you think about if I choose a point outside of those lines, say right there maybe, can you put a neighborhood around that point which avoids the lines? Yes, you can. So this is also a closed set. All right. Here's a weird example. What I want is a spiral that goes outwards, but not outwards forever. It just goes out like to, here's the idea. Start with a circle, and the spiral kind of starts in the middle here, and it goes out. And it just sort of approaches this circle, but doesn't actually get there. It gets kind of infinitely close to that circle, but it spirals outwards forever. Although not out to infinity, but just out to this far. That's what I'm talking about here. Is that set closed? Anybody got any thoughts about that? Because this is a weird example, maybe it won't surprise you. This is not closed. Can someone suggest to me? You have to tell me if you agree with me that it's not closed. You have to tell me some point outside of the spiral where that point does not have neighborhoods which are totally outside of the spiral. Any idea?
Could it be a point on the circle?
Yeah, how about one of the points on this kind of limiting circle here? This is not closed. If I choose this point, say here, it is in the complement because that point is not on the spiral. I said the spiral doesn't actually reach that circle. It approaches it though. So this point here, if you take any neighborhood like that, that neighborhood automatically does intersect parts of the spiral. Actually, the spiral will go through that neighborhood infinitely many times because the spiral is approaching the outer circle. I didn't draw it all the way there, but we'll eventually reach the neighborhood there. All right, so this is not closed because points on the limiting circle have all neighborhoods touching the spiral. All right, so that was a one last weird example. Any thoughts about any of this? This is all about closed sets in R2. All right. I wanted to do just one more example that's a little, well, quite different. How about in this, just an abstract example, we will talk about these every so often. How about just on some set A, B, C, D? Remember, you did some with sets like this on your homework last time. A, B, C, D, and the topology is, I just have to tell you what all the open sets are, and I'm just going to tell you. It's the empty set, B by itself, A and B, C and D, B, C, D, and A, B, C, D. All right. That is a topology. I don't want to check the details of the unions and finite intersections, but this is a topological space. I would like to say, what are the closed sets? Now, the topology tells you what are the open sets, right? Those are all the open sets. But if I know the open sets, what are the closed sets? Which sets are closed? Well, a closed set is the complement of an open set. So if you want to find out what are all the closed sets, you can just start with all the open sets and just take the complement of everything, right? I have here 6 different open sets. That means there will be 6 different closed sets, each one just the complement of one of these open sets. So I'm just going to look at complements of each one, of each open set, right? So to begin with, we have the empty set. What's the complement of the empty set? It would be the empty set is nothing. The complement of the empty set is everything. So the complement of the empty set gives me x minus the empty, x minus the empty set, like that. The complement is x, which is A, B, C, D. So A, B, C, D is closed in this example because its complement is the empty set and the empty set is open. Actually, this fact is true in any topological space because the empty set is always open. It means the full space is always closed. This is a property that is automatically true in any topological space. All right. So that is closed. The other ones will be a little bit more interesting. We have the single element B is an open set, which means x minus B, which would be A, C, D. That is closed. We also, I'm just going across the list here, taking the complement of each one. So AB, the complement, that's x minus AB, would be CD. So CD as a set is closed. X minus, the next one was CD. That is AB. That's closed. The next is BCD. So X minus B, C, and D. That would be just A is closed. And finally, X minus ABCD is the empty set, is closed. So those are all the closed sets in this particular example. They're just the complements of the open sets. All right. One thing I just want to point out here is that, some of these sets are open, some of them are closed. Some of them are both. For instance, AB is open and closed. Right? It is, it's here because the complement of CD. But AB is also one of the original sets in the topology. So AB is open and closed, and also actually CD also, and the empty set and the full space X. These are all open and closed. There's a silly name for that. The set which is open and closed is called clopen. I didn't make that up. And then there are some sets in this topological space which are neither. They are not open or closed, and there's no cute name for that as far as I know. But for example, the set of C all by itself appears in neither list, right? It's not open, and it's also not one of the closed sets that we came up with. So the set C by itself is not open or closed, right? It can be both, it can be neither, or it could be one or the other. All right? This is the basis of the hilarious math joke in the textbook. And I think I will end it there if you don't